Electric charge. Understanding the column. Explore the concept of electric charge, starting with the definition and importance of the column as it is a unit of charge. So let me first ask, what is coulomb? So introduction to electric charge is a unit of charge. The coulomb is the standard unit of electric charge in the international system of units. It quantifies the amount of electricity. So quantifies electricity, muna siya mag-measures the amount of electric charge. So named after Coulomb is honoring Charles Augustin T. Coulomb. Born siya on June 14, 1736 at Angoulême, France, and died on August 23, 1806 at Paris, France. Charles Augustin de Coulomb was a French officer, engineer, and physicist. He is the best known as the eponymous discoverer of what is now called Coulomb's law, the description of the electrostatic force of attraction and repulsion. The fundamental charge of an electron first is electron charge. So, electron charge negative 1.6 times 10 negative 19 is the charge of an electron. Each electron carries a fundamental negative charge of approximately negative 1.6 times 10 negative 19 coulombs. So this value is crucial in calculating electrical properties. So example niya is, in a typical atom, the total negative charge from its electrons is equal in magnitude to positive charge of the protons in the nucleus. And number 2 is the fundamental constant. So, fundamental constant, a key value in physics and electrical engineering. So, in fundamental constants include the gravitational constant, the Rydberg constant, the fine structure constant, and more. So, charge electron, Coulomb constant, Fermi coupling constant, Planck mass, vacuum permittivity is a part of the fundamental constant. Number 3 is the negative charge. So, electrons carry a negative charge because they move from the negative pole to the positive pole of an electric field. So, this is the convention that gives electrons the negative charge. When an atom has more electrons than protons, it has a negative charge and is called an anion. So, if ang atom fewer lang ang electrons than protons nga naay positive charge, maunay gitawag of cation. So next is the electron movement on charge transfer. Number 1 is rubbing. Electrons transfer between materials, so two materials together can cause electrons to move from one surface to another, leading to static energy. Example niya is, rubbing a balloon on your hair transfers electrons, giving the balloon a negative charge and your hair a positive charge. Number 2 is charge imbalance. It creates charged objects. So it occurs when an object has more positive or negative charge than other. So, mahitabo ni siya kung ang electrons move in or out of an object. So, number 3 is ang static electricity. So, muna siya ang common example of charge transfer. Example niya na is lightning. So, when a cloud accumulates a surplus of charge, it can discharge electricity to the ground or to other clouds. So, this can damage structures and vegetation and also kill humans or animals. Next is measuring electric charge in different contexts. So, first, ammeters. So, ang ammeters muna siya mag-measure og current flow. So, it is a device that measures the amount of electric current flowing through a circuit. So, paunsa ang ammeter mag-work? So, it is work to measure direct current, connect the ammeter in series with the circuit. Number 2 is electroscopes. So, muna siya ang mag-detect presence of charge. It is a scientific instrument that detects electric charge in an object. So, paunsa po siya mag-works. So, the test charge moves when an object with an electric charge is brought near the electroscope. So, ang uses niya is mag-use to analyze electrostatic charges and ionizing radiation. So the last one is multimeters. So muna siyang mag-quantify electric potential. So it is a measuring instrument that can measure multiple electrical properties. And also it can measure voltage, resistance, and current, in which case can be used as a voltmeter, ohmmeter, and ammeter. So what it does? So mag-check po ni siya og faulty components. So faulty components is identifies issues like broken connections, faulty components, or incorrect voltage levels. Mag-checks po siya for short circuit na may nana. Static electricity and charge interaction. First is ang attraction. Opposite charges attract. When a positively charged object is brought near a negatively charged object, they will attract each other due to electrostatic force between them. Number 2 is repulsion, like charges repel. So conversely, siya sa attraction, if ang two objects have the same charge, both positive or both negative, they will repel each other, or the force between charges decreases distance or mag-push each other apart. Last is a neutral. Balanced charges. So a neutral object will always be attracted to a charged object regardless of whether the charge is positive or negative, because a neutral object will temporarily rearrange on its own charges to create an attractive force with a charged object. Phenomenon called niya is ang endorsed charge. Next is a real-world applications of electric charge. Number 1 is electronics, circuit design and function. So example niya is ang photocopiers. Ang photocopiers is nag-use siya og static electricity to attract oppositely charged object. Lain pong example niya is ang copying machine and printers. Next is energy storage, batteries and capacitors. So sa balay, example na niya is ang backup power. Energy storage systems can provide backup power for homes. So battery, muna siya ang amount of energy nga mag-store or mag-measured in kilowatt hours or megawatt hours. So supercapacitors is mag-store siya og electrical energy by accumulating charge on their electrodes, similar to regular capacitor. Similar siya sa regular capacitor. So ang regular capacitor is ang mag-store og electrical energy by accumulating charge on two closely spaced surfaces that are insulated from each other. Lastly is ang medical devices, imaging and therapy. Imaging and therapy that involve both imaging and therapy include PET. PET is a position emission topography. Another is a mammography, ultrasound, endoscopy, interventional radiology. So kaning nga devices, muna siya ang mga primarily create detailed image of internal body structures to diagnose conditions like X-rays, MRI, CT scans, and ultrasound. So last is a key takeaways, the importance of the column. Fundamental unit. So muna siya ang column is essential for understanding charges. So na-discuss na ko siya. So first part. Charge transfer explains electron movement and static electricity. Last is wide applications important in electronics, energy, and medicine. That's all. Thank you. In this video, I'm going to show you how I use the PET simulation. So first, we're going to navigate the PET website. So to teach you about the topics like electric field diagrams, electric field strength, and electric potential. So this simulation, it has a lot different features that you can use things that it does to talk about electric fields and then talk about electric potential. So just kind of show you around that simulation here on the top right. You have some check boxes where you can decide if you want to see electric field lines, if you want to see the voltage or the electrical potential, if you want to see values in grid, you can measure within this bar here on the right. This will allow you to measure the electric potential as well as the draw line secret potential, and then you have just a little tip measure over here measuring distance, and then from the bottom you can drag you can drag the bottom these charges anywhere into the space above. So put a couple of charges. Here we see that there is an electric field that is shown emanating away from the positive and going to the negative. That's direction that a positive test charge would feel a force if it were placed in that area. So it's going to be repelled by the positive clearly and attracted to the negative. And so that direction that we get for the electric field, the magnitude of the electric field shown, here is the brightness of the arrow noticed. That it's getting weaker and darker as you get away from the charges. You have the option showing that is just the direction if you don't actually care to see the magnitude. So the voltage will show you the actual voltage as red and blue gradient. So around each of your charges, that remember the voltage is a measure of the amount of energy, so that each unit charge would have if we're placed in that area. So clearly, brighter areas have more energy per unit, so then the darker areas around, if mag-add more charges in one area, it effectively increasing the amount of charge and increasing voltage and the resulting field around it. So, di ba, makita niyo nga mas ni brighter kayo siya if magbutang taog more energy sa iyang per unit. So holding back off so we can take a look at the values now. So di ba mo to nakita ninyo nga if magdungag tagdaghan kayong charges is mas mo darker ang iyang areas around. So if mag-add po tag more charges, ang area po niya is mag-effectively increasing. So what does that mean values? Well, if I put a sensor up, so here then it's going to tell that me with its arrow the magnitude and the direction of the electric field as a vector, the changing length as opposed to changing brightness. So again, para po kuan na to jud makita jud kay nato atong ibalik og butang electric field. So you can see that the direction of the sensor's electric field is going to be perfectly aligned with the one that's already displayed. So but the value of the magnitude of electric field is, diba nakita na ninyo nga the length of the arrow which gets quite big get closer and closer to each of the charges. So going away from the positive and going toward the negative, the values checkbox allows you to turn that on or off, showing the actual numerical values of the sensors. So diba makita ninyo dira ang yang sensors is now grid siya of the electric field. Diba muna makakuan po na ang sensors magud is parang po makatabang po siya ma-align, o if dili pa ka satisfy sa iyang alignment o pwede ka mag-use og tape measure. If dili pa ka satisfy sa iyang alignment, di ba, you can use tape measure na sa ubos sa equipotential. So next is the grid line. So ang grid line is nagguan siya og 10 cm. So ang little boxes niya is 10 cm pod, og as you can could align your charges very nearly perfectly on those and be able to make some precise measurements. So without too much difficulty, if mag-need na ka og some measurements nga not on the grid line and you're not using the grid, then you can use the tape measure also and be able to measure distance in this graph or on the screen precisely. So later we can drop it off. Kung dili pa pud ka satisfy adding sensors or kaning grid line is mo to para mahibalaan jud nimo ang yang centimeter is magamit na jud kag tape measure. So dako pug help ang tape measure no, kay inig mo siyang ikuan man gudra makuan dayon nimo kung pila jud ang iyang measurement. Mas dali nimo makuanan ang measurement niya kaysa aning sensor. If kaning sensor mo gamiton, mas ang tape measure man gud is makita na nimo ang yang alignment o makita pud mo og pila ang yang centimeter, di ba? O di ba makita ninyo kung unsa jud ka align kung unsa jud ka align ang naa sa ang kanang gisukod, di ba? Okay. Next is the equipotential. Okay, ang equipotential tool mo ni siya ang able to measure the voltage value. So just like the voltage, nagpakita po siya. Notice nga if mag closer na ang voltage, so mag-getting bigger and bigger po ng amount of energy. So ang per unit charge niya is what the voltage is the equipotential or the electric potential. And the equipotential will actually show me a lines where all of the lines, all of these positions around here have the same. So the amount of electric potential, so mag-connect ko ni siya, and after that kunin mo ang iyang voltage is pwede na ka maka-draw sub ka, so you can draw these lines at different voltage, so and they behave kind of like the contour lines. So mana diba, makuhanin mo ang iyang voltage bitaw if kuan man good, if imong i-get closer to negative jud ang kanang equipotential, imong jud i-get closer to na negative, actually ang negative voltage man good is more like valleys or holes. So ang kaning positive charge man good is more on in the same way siya sa negative, but ang iyang topographical analogy and in positive charge are more po siya like mountain top. Okay, diba? Makita man sa na kana. So para mawagtang to ang green nga nag-circle sa charges is tutulungan ng nimo ang erase button nga nasa potential. So para po mawagtang ang electric field, kuon po nimo sa checkbox ang check nga nasa electric field, and also katong grid, katong gagmay nag-square nga kuan, para di po sa nimo siya makita, kuon po nimo sa checkbox also ang voltage. So ang nabili na lang is values eh. As you can see, ang nabili na lang nasa checkbox is ang values. So that's all for the charge and field simulation. Thank you.
Hello everyone, so I am going to continue the discussion about this electric charge and field. So now let us talk the electrically neutral atom. So before going to that, let us first define what is an atom. So an atom is the smallest particle that has the properties of an element. So it is defined as the smallest unit of an element that retains the chemical properties of that element. And it is made up of three types of particles, namely the protons, neutrons, and electrons. When we say electrically neutral atoms, it refers to the atom that has an equal number of protons. So protons are the positively charged and electrons are negatively charged. So this balance ensures that the overall charge of the atom is zero. So if an atom gains or loses electrons, it becomes an ion and it is no longer electrically neutral. So an example for this is when a hydrogen atom has one proton and one electron. So since the number of positive and negative charges is equal, the atom is electrically neutral. Because the positive and negative charges cancel each other out, it remains neutral. So next up, we have the charging by friction. So let us first define what is this friction. So friction is a force resisting the motion of two materials relative to each other. It is generated when one object, fluid, or material is moved relative to one another and always acts in the opposite direction of the motion. So for you to be able to understand it easily, here is the best description that I have found on the internet. So, friction is a force that resists the sliding or rolling of one solid object over another. So, another definition is it is a force felt between two surfaces when one attempts to slide against the other, whether or not they are moving. So it always acts to slow things down. When objects are rubbed together, they acquire equal and opposite charges due to the transfer of electrons. So this process is known as the triboelectric charging, which results in one object becoming positively charged and the other relatively charged. So this charging by friction works when two objects or often insulators come in contact and are rubbed together. When this happens, electrons are disturbed at the atomic level. One material has a greater affinity for electron and gains them, becoming negatively charged. The other material loses electrons and becomes positively charged. So in charge separation, once they separated, the object retains their opposite charges as insulators do not readily allow charges to move away. So an example of charging by friction is when you rub a balloon on the hair. So the balloon gains electrons, which is a negative charge, while the hair loses electrons, positive charge, causing the hair to stick to the balloon. Another example is when dragging feet on a carpet. So the carpet transfers electrons to a person's body, leading to a static shock when touching a metal object. We have to also remember that the process of charging by friction only works well with insulating materials because conductors allow charge to dissipate or lose. Now let us have the insulators. These are the materials that do not allow the free flow of electric charges. Unlike conductors, which are enable electrons to move easily, insulators restrict electron movement, preventing the transmission of electricity. So personally, I've learned this when I was in grade 3 about the insulators and conductors. And these insulators are the ones that restrict electric flow from like a material that contains electricity, and the conductors is from the word itself, it conducts electricity. So a common example is the rubber. So rubber is a common insulator used in electrical wiring and safety equipment since it prevents the electric current from passing through. That reduces the risk of electric shock. These insulators are essential in electrical engineering and everyday applications, whether in home, school, or everywhere, because it controls the flow of electricity, which is necessary for safety and efficiency. Now we will have this as a unit of electric charge. So this was already discussed earlier, but yes, I'm going to repeat the SI unit of electric charge is the coulomb. So one coulomb represents the charge of approximately 6.242 times 10 raised to the 18 electrons. So this unit is essential in quantifying the transfer of charge in electrical circuits and various physical processes. Next, we have the charging by induction. So this process is generating electrical current in a conductor by placing the conductor in a changing magnetic field. So it is called induction because the current is said to be induced in the conductor by the magnetic field. So when two objects are charged by induction, they acquire opposite charges without direct contact. This occurs when a charged object is brought close to a neutral object, causing a redistribution of charges within the neutral object. So example, if a negatively charged rod is brought near a neutral metal sphere, the side of the sphere closest to the rod becomes positively charged, while the far side becomes negatively charged. This separation of charges allows for an induced charge when the sphere is grounded or separated. Another example for an induction is when a magnet is brought towards a coil, a relative motion is generated between the two due to a magnetic flux. This leads to an electromotive force which results in an electric current in the coil. The effect of humidity on charge accumulation. So when we say humidity, it is the amount of the concentration of water vapor in the air. So the humid air contains water molecules that act as conductors, allowing charges to neutralize more quickly. So on dry days, these objects become charged more easily because dry air prevents charge dissipation. So if you can observe that when someone touches a water, dali ra sila makurintihan, and that is because the water molecules are, known as conductors. Now moving on to the charge of a proton. So a proton carries a charge of positive 1.6 times 10 raised to the power of negative 19 coulombs, which is equal in magnitude but opposite in sign to the charge of an electron. So if you can remember when we listened to the previous discussion, that proton is the positively charged ion and that electrons are the negatively charged ion. So example, in a hydrogen atom, the single proton in the nucleus is balanced by the negative charge of a single electron, making the atom electrically neutral. And now let us find out who is the scientist that is credited with naming the electric charges. So now we have Benjamin Franklin, which introduced the terms positive and negative to describe electric charges. His pioneering experiments with electricity helped establish the foundation of electrostatics. His famous kite experiment demonstrated that lightning is a form of electricity, furthering our understanding of electric charge. Now let us go back to the friction. Let's talk about the factors affecting charge transfer by friction. Several factors influence how much charge is transferred during frictional contact, and it includes the type of material used, temperature, and the surface roughness. So when we say type of materials, some materials have a greater tendency to gain or lose electrons, the triboelectric effect. And in temperature, higher temperatures can increase electron movement, affecting charge transfer. And in the surface roughness, smoother surfaces tend to transfer less charge than rougher surfaces. However, gravitational forces do not affect charge transfer, as frictional charging is a surface phenomenon independent of weight or mass. So an example for this one is rubbing a balloon on wool transfers charge because wool readily donates electrons, whereas rubbing a balloon on a smooth metal surface may not produce as much charge due to the differences in electron affinity. And lastly, let us talk about the formation of ions. But before that, let us know what is ion. So ion is any atom or group of atoms that bears one or more positive or negative electrical charges. So we have the two types of ions, the positive and negative charged ions. So the positively charged ions are called cations, and the negatively charged ions are called the anions. When an atom loses or gains electrons, it becomes an ion. And this process changes the atom's charges and affects how it interacts with other atoms in electric fields. So the cation forms, or the positively charged ion forms when an atom loses one or more electrons. However, the negatively charged ion, or the anion, is formed when an atom gains one or more electron. So for us to have a better understanding about cation and anion, Cation is the positive charge ion that loses one or more electrons, and the anion is a negatively charged ion that gains one or more electrons.
So now let us proceed with the topic called insulators and conductors. So before we get to knowing what is insulators and conductors, let us first know what is electricity. Electricity is the set of physical phenomena associated with the presence and motion of matter possessing an electric charge. It is a movement of electrons called electric current in a circuit. So in short, electricity is found in the electron flow. It is the electricity is a flow of electrons around a circuit. So it powers any appliances that we can find that needs electricity. So that is electricity. So some materials are good at passing current through them and some materials block the current, and these materials are called the conductors and the insulators. So conductors are materials which allows electrical current to flow through them easily, while the insulators are materials which are poor conductors and do not allow electrical current to flow through them easily. So how well a material conducts depends on the number of free electrons. So for now, let us learn about the conductors first. So a conductor conducts electricity since it offers little or no resistance to the flow of electrons, thus leading to a flow of electrical current. So conductors are the materials which provides the easiest path to the electric current. So the current smoothly travels through the conductors, and the conductors provide a good path to an electric current because they suppress free to move electrons in their atoms. So example is playing a video game in a computer, then the electric wires that connects to the outlet and the computer are called conductors. So electricity that is coming from the outlet, the source of electricity, will travel through a conductor, which is the electric wires, which will then provides or powers up the computer. So that is an example of a conductor. It is the electric wires. So the materials that are a good conductors are metals, silver, and copper. So metals are good conductors. They contain loose electrons. Silver, most conductive metal. It is precious and costly metal. So copper is cheaper and a good conductor. So as you can see from the picture, there is electrical flow which is flowing from the battery to a conductor. So that is how electricity is able to flow through a conductor because a conductor is good at what do you call this? Good at keeping the flow of electrons. So that is a conductor. So the benefits of using a conductor is conductors have very low resistance, making the electric current move easily, meaning using conductors with very low resistance save electricity. So the most useful and common used conductors for electric wires are silver, copper, gold, and aluminum. So in this picture, we can see a resistance which is red. It's because if a high resistance conductor is selected, then it will become piping hot when electric current will flow through them. So this will waste so much electricity in heating the conductor that would have powered some appliances. So meaning using conductors with very low resistance save electricity. Wires. So the most useful and common used conductors for electric wires are silver because it is the best of the conductors but very expensive and it oxidizes easily. So printed circuit boards and TV screens are a few things where it is used. So for the copper, home wiring is usually used or usually made of copper because it has a good amount of free electrons which can conduct electricity. And gold is, it has lower resistance but very expensive. It is used in cell phone circuit boards and computer chips. And lastly, aluminum. This conductor is usually used in long but about 40% less conductive than copper. So now let us move with the insulators. So insulators are materials that reduce or prevent the transmission of electricity, heat, or sound. So it's like the opposite of the conductor. So an electric insulator or a bad conductor is a material in which electricity current does not flow through an electric current. So materials like glass and rubber have very good insulation. So if anybody unconsciously touches, they won't get electrocuted. That is the purpose of an insulator. So example is like the wire of your charger. Our wires are made of metal in the inside, which is a conductor, but the outer layer of our charger is made of rubber, which is an insulator. That is why when we plug or unplug our charger, we won't get electrocuted because we are protected with a rubber layer or the skin of our charger. So that is an example of an insulator. It shields us from being electrocuted. So there are different types of insulators. There are porcelain, rubber, plastic, paper, wood, and glass. So what happens when a charged conductor is brought into contact with a neutral conductor? So when a charged conductor is brought into contact with a neutral conductor, the neutral conductor will acquire the same charge as the charged conductor. So it means that when a charged conductor is brought into contact with the neutral conductor, ang mahitabuan na is katong duha ka conductor, same ra dayon ilang level of charges. So, essentially, sharing the charges between them due to the free movement of electrons in both conductors, this process is called charging by conduction. So, what is a semiconductor? A semiconductor is a material that can conduct electricity under certain conditions. So, semiconductors are used in many electronic devices, including computers, smartphones, and medical devices. So here are some examples of a semiconductor devices: the op-amp, the ICs, the transistors, the resistors, the capacitors, and the diodes. So how do semiconductors work? Semiconductors work by enabling the valence electrons, those located in the outer shell of an atom, to bind with the valence electrons of the other atoms. So there are types of semiconductors. The N-type, which carries current mainly as negatively charged electrons, while the P-type is it carries current predominantly as electron deficiencies called holes. Uses of semiconductors, transistors, and diodes are made out of semiconductors. So, semiconductors are used in medical devices, clean energy, transportation, and defense. Semiconductors are also used in rice cookers, LED lighting, displays, gaming devices, and blood pressure monitors.
So now we will talk about electrostatic equilibrium. So when we say electrostatic equilibrium, it is a state where charges within a conductor are at rest and there is no net movement of charge. So it's like a peaceful state where charges are not moving around. So imagine a group of people all pushing and shoving each other. Eventually, they'll settle into a steady state where everyone is pushing equally and no one moves. So this is like electrostatic equilibrium for charges in a conductor. So why do we need to understand electrostatic equilibrium? So understanding electrostatic equilibrium is crucial for analyzing how charges behave in conductors and for designing devices that use static electricity. Now let's move on to the key characteristic of electrostatic equilibrium. Zero internal electrical field. So the electrical field inside a conductor in equilibrium is zero. So which means no moving charges. Charges in a conductor at rest, like those people finally stopping their pushing. So we go back to our example in the people in the bus. So those people finally stopping their pushing. That is why no moving charges, which means zero internal electric field in the conductor. Now we have the charge distribution. Charges reside primarily on the outer surface of the conductor. So when we say charge distribution, the electric forces inside the conductor balance out. So there's net force in any charge. So let us go back to our example again with the people in the bus. So when we say charge distribution, it's like the people pushing each other equally. Nobody gets pushed around. So they have equally forced, pushed, so nobody gets pushed around. So next is we have the constant potential. The electric potential is constant through the conductor. So what does it mean? So light charges repel, so they spread out as far as possible, ending up the surface on the conductor. So again, let's go back to our example, which is the people at the bus or in the bus. Think of the people pushing each other to the edges of the room. So that is how constant potential. So electric potential is constant throughout the conductor. Now we have why is the electric field inside zero? So repulsion is like charges. So when we say charges within the conductor repel each other. We also have free electrons. The reason why electric field inside is zero. So conductors have free electrons that can move easily. We have also the charge distribution. So charges within the conductor will move position where they are as far apart as possible, creating a balanced distribution, which causes the electric field inside zero. So the movement of charges ensures that the electric field inside the conductor cancel out through zero electric field. Now we have why charges hang out on the surface. So why does? So it's because of the repulsion of like charges. So like charges repel each other, so they naturally move to the outermost surface of the conductor. Now let us continue to the Van de Graaff generator, which when we say Van de Graaff generator, a charge storing machine. So Van de Graaff generator is device that builds a large static charge of metal sphere. So it's a classical demonstration of electrostatic principles. So how does it work? So charge transfer. So the belt. So Van de Graaff has a belt, so which picks up charges from a source like rubbing against a brush and carries them to the sphere. So charge accumulation is the charge built up on the sphere, creating a high voltage. So example of this one is the hair raising experiment. So the hair raising effect is if you touch the sphere, the charges can jump to your body, making your hair stand on. And so that is the reason why your hair raised when you touch the Van de Graaff. It's because of the belt or the charges build up on the sphere, creating a high voltage, which causes your hair to stand. So next is we have the electrostatic shielding. So blocking electric fields. So when we say conductor can act like an electrostatic shield, blocking external electric fields from penetrating its interior. So a conductor can block external electric field from reaching its interior. So it's like an umbrella stopping from the rain. So imagine you're trying to keep someone from a rainstorm. So you could use an umbrella to shield them from the rain. So that is how the blocking electric fields. We also have electrostatic shielding, which is Faraday cage. When we say Faraday cage is a conducting cage that shields its interior from external electric fields. It used to protect electronic devices and even people from lightning strike. So how does it work? So a Faraday cage is a metal enclosure that blocks electrical fields. It's used to protect sensitive electronics and even people from lightning strikes. So example of this one is a car, which is if the lightning strikes a car, the electricity flows through the metal of the body and out of the ground, so protecting the people inside. We also have the induced charges. So when we say induced charges, we have the magic of polarization. When you bring a charged object near a neutral conductor, the charges in the conductor rearrange themselves. So a conductor temporarily becomes polarized, so the side closest to the charged object becomes positively charged. So, have you remembered the magnet and it brings it near a piece of iron? So the iron will become magnetic, even though it wasn't magnetic force. This is similar to induced charges like the balloon in a wall. So when you rub, or even a ball pen, which is rub in your hair, it picks up charges. So when you bring the charge of the ball pen to a balloon or a paper, so the paper will temporarily become charged and attracts the ball pen. So in short, when you bring a charged object near a neutral object, the charges in the conductor rearrange themselves. So the side of the conductor closest charged object becomes positively charged like the iron becoming magnetic. We have also the grounding, which is grounding connects a conductor to the earth. which acts like a huge reservoir of charge. So excess charge flow. If a conductor has excess charge, it can flow on the earth, making the conductor neutral. So grounding is like a connecting conductor reservoir. We also have the lightning rods. When you say lightning rods are grounded to protect the building from lightning strikes, they finish this. So we also have the charge flow. If a conductor has excess charge, it can flow on the earth, making the conductor neutral. And lastly, we have the safety. So grounding is used to protect people and equipment from electrical hazards. So we can see grounding in our mostly of our appliances. So example is lightning rods are grounded to protect building from lightning strike. So the lightning strike the rod and the charge flow through the rod to the ground, preventing damage of the building. So when we say grounding, it is also like the electrostatic shield. So with the lightning strikes, so it will just move through the metal body to the ground and it won't affect anything. It's because the charge will flow to the ground. So in summarization, when we say electrostatic equilibrium, charges in a conductor reach a balanced state and remain at rest. We have also, don't forget, the characteristic include zero internal electric field, charge distribution to the surface, and the constant potential through the conductor. So the proportion between like charges drive this distribution and how grounding allows excess charge to flow. So when we say electronics, electrostatic principles are fundamental design of capacitor which store electrical energy and other essential electronic components. And lastly, safety. So understanding grounding and electrostatic shield is crucial for protecting people and equipment from electric hazards such as lightning strikes. So that would be all for my report in electrostatic equilibrium.
An equipotential charge refers to a distribution of electric charge where the electric potential is the same at every point. In other words, the electric potential is constant throughout the region. In simple terms, it's surface where a charged particles would not experience any net force because of the potential energy at all point is equal. In electric field, potential energy changes as you move through the fields. However, along an equipotential surface, there is no change in electric potential energy, meaning no work is required to move or a charge along this surface. Equipotential surfaces are always perpendicular to electric field lines. For example, around a point charge, the equipotential surface are spherical shells centered on a charge. There are characteristics of equipotential charge. The first one is the constant potential. The electric potential is the same at every point in every region. And it can happen in two scenarios. In number one, in a uniform electric field, and number two, in an conductors. Number 2. Zero electric field. The electric field is zero within the region, as there is no potential difference. This means that the electric field intensified at the location is zero. Several scenarios can lead to zero electric fields. The third one is the no net force. A test charge within a region would experience no net force, as the electric field is zero. In the context of the electric fields, this implies that the sum of the individuals' forces acting on a charged particles due to the electrified field or gravity or etc. If there's a characteristics, then there are also examples of equipotential charges. The first one, conducting spheres. A conducting spheres with a uniform charge distribution is an equipotential surface. These spheres are commonly studied on electrostatics because of how charge distributes themselves on conductors. The second one is the parallel plates. Two parallel plates with equal and opposite charges form an equipotential region between them. This commonly studied in the context of capacitors and electric fields. The third one is cylindrical surface. A cylindrical surface with a uniform charge distribution is an equipotential surface. A cylindrical surface refers to the three-dimensional surface that wraps around a cylinder, and it can be used in electrostatics or other fields of physics to describe specific types of symmetry or field behavior. The fourth one is equipotential charges or perpendicular equipotential charge. It refers to the configuration where two or more equipotential surface intersects at the 90-degree angle forming a perpendicular relationship. An equipotential surface is a surface where an electric potential is the same at every point, meaning no work is needed to move a charge along that surface. An equipotential spherical surface is a spherical surface where electric potential is the same at every point. This occurs with spherical objects such as conducting spheres and charged uniformly. These types of surface is commonly seen in electrostatics, particularly around spherical charge distribution like a point charge or a uniformly charged spherical shell. There are also importance of equipotential charge. The first one is electrostatic shielding is an equipotential surface can be used to shield sensitive equipment from external electric fields. The conducting materials, often in the U forms of metal blocks, electric field from penetrating into enclosed region, preventing the electric field from affecting sensitive equipment or environments. Number 2, electric field calculations. Equipotential surface can simplify electric field calculations as the potential is constant. The electric field is defined as the force per unit charge exerted on a small positive charge placed in the field. The third one is distribution or the charge distribution. It is an equipotential surface that can help determine the charge distribution on an object. The equipotential surface are regions where the electric potential is the same everywhere. In summary, an equipotential charge refers to the distribution of electric charge where electric potential is constant through the region, resulting in a zero electric field and no net force on a test charge.
Good day, everyone. Now let's move on to the electric field lines and equipotential surfaces. Electric field lines are the imaginary lines show the direction in which a positive test charge would move if placed in the field. These help visualize the distribution of charges in the system, and they represent the direction and magnitude of the electric field at various parts in space. Charge moves perpendicular to electric field lines when changing equipotentials. This describes the movement of the charge across equipotential surfaces in an electric field. In a uniform electric field, the equipotential surfaces are parallel planes, or shall I say, uniform fields have parallel plane equipotentials. Why? A uniform electric field has the same magnitude and direction at all points. The electric field lines are straight, parallel, and evenly spaced. So since the electric field is always perpendicular to the equipotential surfaces, and the field lines in a uniform electric field are parallel and straight, the equipotential surfaces must be planes that are also parallel to each other. So in a uniform electric field, these planes are spaced evenly in the direction perpendicular to the electric field lines. So what happens to the equipotential surfaces as the distance from a point charges increases? The equipotential surfaces spread out and they become further apart as the distance from a point charges increases. Move away from the point charge, the electric potential decreases because the influence of the charge weakens with distance. Electrical potential describe the potential difference in electric potential energy between 2 points in an electric field. It says here that if there is no potential difference, there is no change in the potential energy of the charge. Work is done when there is no change in potential energy because the potential difference is zero. No work is required to move the charge. So the work required to move a charge between 2 points on the same equipotential surface is zero. Moving a charge along an equipotential surface does not require any work because the electric field does no work on the charge when it is moved along a surface of constant potential. If the electric potential at a point is zero, what can be concluded about the electric field at the point? So if the electric potential at a point is zero, it doesn't necessarily imply that the electric field at a point is also zero. If the potential is zero at a specific point, but the potential changes rapidly in nearby locations, the electric field at that point can still be a non-zero. For instance, the potential could be zero at a point and increase or decrease in the surrounding region, leading to a non-zero electric field. In a nutshell, a zero electric potential at a point does not automatically mean that the electric field is zero at that point. The electric field would only be zero if the potential is constant in a region, meaning there is no change in potential anywhere around that point. At this juncture, we have here the equation represents the electric potential W due to a point charge Q, where V is equal to KQ over R. So this equation defines the potential due to a point charge. This equation also shows that the electric potential decreases with increasing distance from the charge, where V says that it is the electric potential at a distance r from the point charge. K is the Coulomb's constant, 8.99 times 10 raised to the power of 9. Q, the charge creating the electric field. R is the distance from the charge to the point where the potential is being calculated. So I have here an example. A point charge of Q is equal to 5 times 10 raised to the power of negative 6c is placed in space. Find the electrical potential at a distance of 2 meters from the charge. By the use of the formula, V is equal to KQ over R. So here's the given. K is equal to 8.99 times 10 raised to the power of negative 9. The Q is the charge, 5 times 10 raised to the power of negative 6c. And the R is the distance is 2 meters. So V is equal to 8.99 times 10 raised to the power of 9 times 5 times 10 raised to the power of negative 6 divided by 2. So 44.95 times 10 raised to the power of 3 is divided by 2. So the electric potential at a distance of 2 meters from the charge is 22.475 kV or 22,475 volts. Here's the difference of the positive charge and negative charge. So the positive charge is a region around a positively charged particle or object where the electric field is directed radically outward. So it has an excess of protons and a deficiency of electrons. So it moves from high to low potential. So a positive test charge will experience a force in the direction of the electric field. So as the charge moves along this direction, it is moving toward a region of lower potential and its region in a decrease in the potential energy of the charge. So while the negative charge is a negatively charged particle or object where the electric field is directed radically inward. So it has an excess of electrons and a deficiency of protons. So it moves from low to high potential. So the negative charge moves in the direction opposite to the electric field because it would experience a force pointing from low potential to high potential, meaning it moves towards region of higher potential. So now let's move on to the potential difference. So what is potential difference? Potential difference is a factor that triggers the flow of electricity between 2 points. This is also known as voltage. So it is expressed in an equation here below. Potential difference is equal to work done over charge. So if the potential difference between two equipotential surfaces is increased, what will happen to the electric field strength? A greater potential difference means a stronger field. So, a stronger electric field exerts a greater force on charged particles, and these charged particles accelerate faster in a strong electric field. A strong electric field can transfer more energy to charged particles. A greater potential difference often corresponds to a higher voltage. A stronger electric field
can lead to an increased current in a conductor. A stronger electric field can also produce more powerful effects, such as greater electromagnetic induction or more intense electromagnetic waves. So, in a nutshell, a greater potential difference leading to a stronger field means that the electric field has more energy, exerts force. So now we are on the last part of the report, equipotential surface. So it is a surface where the electric potential is the same at every point, resulting in no electric field or potential difference between any 2 points on the surface. So how equipotential surfaces are formed? When multiple charges are present. There are two bullets here. First, the equipotential surfaces are no longer perfectly spherical because they result from the combined potentials of all charges. Next, the exact shape and spacing of these surfaces depend on the magnitudes, signs, and positions of the charges. So, while the equipotential charge is a charge that has the same electric potential at every point, meaning that there is no net electric field or potential difference between any 2 points.